we're on the clock. So hopefully you spent the time and watched the video. So what we're going to do today is do a quick review of the material that was covered in the video, and we're going to spend most of the class period working the problem at the end of the chapter. Okay? So that's kind of where we're at. There was a couple of slide overlap or lack of overlap between where we were last year. So I'm going to go back and cover those, talk about those slides because this wasn't talked about. So the last thing that we were at on Monday was talking about the difference in electronegativity to determine what type of bond we had. We can use that to distinguish if it is a pure covalent, and that means the difference of electronegativity is going to be 0. A nonpolar covalent means the difference is 0.1 to 0.4. A polar covalent, which is going to be 0.4 to, well, we've already got 0.4, so I'd say this one should be 0.5 to 1.9. And if it's 2.0 or greater, that means that it's ionic. So this is kind of a summary of what that table of what we just had on the previous page. I just want to look at a couple of examples of this. So pure covalent is I guess it's pure covalent in my mind is difference of 0. We say pure covalent. So you have nonpolar. I classify these as two different things, and the book says that they're the same thing. You have nonpolar covalents that are less than 0.4, and then you have polar covalent where you've got an unequal sharing of electrons. That's where you end up with partial positive and partial negative charges. That's between the 0.5 and the 1.9. And once it goes greater than 2, then you have transfer of the electrons and you form the ionic bonds. All right, so if we look at these, which one of the pair would form an ionic bond? So you got the table of the electronegativities. Which ones are going to come together and make an ionic bond? Skippers today. Okay, a couple more. All right, everybody's in. And I tell you this one, you could answer it a couple of ways. Almost everybody said it was choice D, which right one. Yep, choice D is certainly the correct answer. The difference in electronegativity between strontium and fluorine. So strontium is a 1, fluorine's 4, so the difference was 3. That's the way that this problem set up to answer. What's the other way you could answer this? Metal and a non-metal, exactly. So recognizing you had one thing that was a metal, and the other side you had a non-metal. That's the only thing. Everything else were non-metal pairs. So there's a couple of different ways that you can approach knowing how those things are formed. Okay, so now we're going to just quickly go through here and talk about some of the things that were in the notes that hopefully you've already watched. And this is where it's going to be in your advantage if you watch them, because you're going to answer the same clicker questions you saw yesterday if you watched them. If you didn't, you're taking a blind guess. So, all right, here's one. we had another person come in. Okay, everybody in? All right, see what we got. All right, well, I hope it's not A. Let's see. So most of you think it's either D or B, and it's D. So if we look at this in increasing bond polarity, anything binding to itself is going to be pure covalent. So that makes sense that choosing the ones that have this one being the least. And then you need to start looking at going in the orders of the biggest separation. Fluorine is lower down, or it has the greatest electronegativity of anything. So HF is going to be more electronegativity difference than HBr. And then finally, you look at the last one where you have the ionic compound. It has by far the greatest difference in electronegativity. Whenever you have salts formed, those are the most polar things that you can have. Okay, let's look at the next one we had. So this is material that I've already showed you. We're going to go over the Writing-Lewis structures again. A lot in some of the sample problems that we're going to work at the end of the chapter. These are just the general rules that we talked about in the video. So you write the correct skeletal structure. Sometimes you don't know it always is correct. So sometimes you have to take some guesses at it. But hydrogens are always terminal. Okay, so that's one thing we have. The more electronegative atoms always going to be placed in terminal positions. So the least electronegative is going to go towards the center. If we calculate the number of electrons that we have by summing up all the valence electrons for all the atoms in that particular molecule, then we want to distribute the atoms around to try to create octets, duets in the case of hydrogen, to as many atoms as possible. And if anything has an incomplete octet, then we need to form double or triple bonds by collapsing electrons in. And we'll look at lots of examples of that. Here's one of just the important things to understand, what we call bonding patterns. So if we look at bonding patterns, here are some things that we always are going to find. Carbon wants to have 4 things bound to it and 0 lone pairs. So this is the way we want to find carbon. And the ways that we can find carbon are these 4 single bonds, or we can find carbon with 2 double bonds that has 4 things bound to it, 4 pairs of electrons shared to it. We could also have a single bond and a triple bond. Can you think of another one? Two singles and a double. So those are the 4 possible ways that we'll find carbon in nature. All right? And going back to something that's talked about later in the chapter, all of these, if it's in one of these ways, it has a formal charge of 0. So when you start putting all this stuff together to help figure out what's the best structure, we choose the ones that have formal charges of 0. Okay? All right, when we find nitrogen, so nitrogen is usually represented as a blue atom. Nitrogen is found with 3 things bound to it, and most commonly with a lone pair. Nitrogen is not as picky as carbon, because the ways that we can accomplish that are the ways that are shown below. Then we could also do a single and a double bond in a lone pair. We could also do a triple bond in a lone pair. And occasionally, these are the ones that have a formal charge of 0. We'll stick with that. Formal charge equals 0. So those are the most stable forms, but occasionally we'll find nitrogen in a form that has 4 things bound to it, but it's a +1 charge when that occurs. All right, again, hydrogen and the halogens are always terminal. So they have a single bond to them, and with that fulfills their octet. They have 8 electrons around those. So those are always going to be on the outside. Boron sometimes will have 3 things bound to it. It's happy if it doesn't have a full octet. It can bind with something to have a full octet, but it can live without it. Just recognizing those structures make life a little easier for you as you go forward. Okay, so I went over this one in the video. We're going to do a lot more of those in the notes that are coming up here. All right, so the structures, blah, 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 blah. I've already done all those. Oh, there was yours. Again, you watch the video, you know the answer. So which one's the best Lewis structure? Just based on to tell you what we talked about today, which one has the bonding patterns. And the way the bonding patterns work, if you know the atom in the top row, everything underneath it behaves the same way. Last one. All right. Let's see. Most popular answer is D. That is indeed the correct answer. Well, another way that I could look at answering this one, if I couldn't do the Lewis structures, is look at who has a octet and who doesn't. So if I look at the first structure, this one has 10 electrons around it. That's not an octet. Okay, this one only has 6 electrons around it. That's not an octet. This one only has 4 electrons around it. That's not an octet. This one has 8. This one has 8. This one has 8. So I choose the one that's correct. Okay, it's the best Lewis structure. Everything's trying to get an octet. All right, I talked about resonances in the videos. You have more than one form. We'll work several problems with that. The thing about resonances is it's not one or the other, it's a combination in between the two things. And you take organic chemistry, you're going to learn that a lot of things occur as resonance ions. It's a blend between the two possibilities. Formal charge is what we use to help distinguish which is the best Lewis structure. Okay, so formal charge is a simple formula. It's the number of valence electrons less the number of non-bonding electrons less 1/2 the number of bonding electrons. Okay, if it's a neutral molecule, the sum of all the formal charges has to equal 0. If it's an ion, the summation of the formal charges has to equal the charge of that ion. And don't get formal charge confused with oxidation number. Okay, but what we want to do is we want to try to get things to have a formal charge of 0. That's most stable. And then if it's things that are not 0, we're going to put the most negative formal charge on the most electronegative atom. Okay, so went over these already. Some of you watched it, some of you hadn't. It's your choice today. Okay, so which set gives the correct formal charges? So I give you at the bottom, I give you the formula for formal charge. So which one's the correct set of formal charges? need one more. All right, I think that's it. All right, everybody's in. We're a little bit more mixed on this one. So most of you said B, but C was right behind it. It was B. Okay, let's look at the formula on how you would use to calculate those. Okay, so the formal charge is equal to the number of valence electrons less the number of paired or unpaired electrons. So if I'm looking at sulfur, there are 4 electrons here, so less 4, less 1/2 the number of bonding electrons. There's one double bond. How many double electrons is in a double? 4. Yeah, it's 2 pairs or 4 electrons. So if I look at this one, so I've got 6 less 4 less 2. The sulfur's formal charge is 0. Okay? And at this point, I can go ahead and stop it because the only one that has sulfur at 0 is choice B. But we'll go ahead and do the other ones for the heck of it. So carbon, there's no unbonded or unpaired electrons because they're all paired, less 1/2. All right, so I've got 2 double bonds. How many electrons does that represent? Each double bond we just said represented 4. There's 2 of them, so that's 8. So if I subtract that out, it's 0 as well. Okay, so that makes sense. And look at nitrogen at the bottom. So it's 1/2. I've got lone electrons. If I look at the lone electrons, I've got 4 of those that are unshared electrons, less 1/2. And I've got 1/2 of the number of shared electrons, 1 double bond, which is 4. So that's going to be minus 2. So I've got minus 1. And all of those add together to be the charge of this polyatomic ion is a minus 1. All right. You'll have a test question where it's going to be identifying the formal charge or choosing the formal charge with structure. Okay. Yeah, we're going to work problems like that. I don't even want to. We talked about exceptions to the octet rule. And then the end of the chapter looks at bond energies and trends in bond energies. The big thing that I'll just point out in this quick recap is looking at triple bonds have more energy than double bonds, which have more energy than single bonds. And you see that trend repeated regardless of what it's connected to. And the other thing we see is that the shorter the bond, the stronger the bond's going to be. So something like a bromine with a fluorine is the smallest atom, has a greater bond energy than bromine to chlorine. So chlorine's going to be getting larger. And then bromine with itself is even further down, so it's a larger atom. It gets a little weaker still. Okay, so you'll have a question. Choose the greatest bond energy, choose the weakest bond energy based on atom size. So that'll be one of the things. And this is a table that compares those. And then the last thing that's talked about here was looking how to calculate the enthalpy of a reaction by doing the summations of the bond energies that are broken, right? Less the bonds that are formed. And we apply that using Hess's law. To use this, we just look the values up out of the table. We look what these bond energies are, and we calculate for all the bonds. You got to be able to draw Lewis structures, or you can't know which bonds are there. So if you don't get your Lewis structure right, the rest of it's not going to make much sense to you. So Lewis structures are the important things we take forward out of this. I did this example in the notes already, so I'm not going to do that again. And then bond lengths are related to bond energy, and it compares those things out. And the last thing just talked about the metallic bonds. Okay, so we're just going to roll right in to start working some problems out of Chapter 9. We're not going to get through all of these today by any means, but we're going to get a good start on. Remember, you've got the Mastering Chemistry that's due Thursday night, tomorrow night, yeah. Again, if you didn't commit the time to watch that video, I strongly encourage you to do it. So, see what you missed in terms of all the notes. So problem number 36 is writing out the electron configuration. The other thing I'll tell you, send an email out on it. Maybe you're not checking your email, but I posted the table that you'll get on the exam, as well as I posted a study guide yesterday. So those things are available for you to start looking at in your studies. So we want to be able to write electron configurations, and from electron configurations, we want to go to a Lewis symbol for neon, and then show the electrons from the electron configuration that are included in the Lewis symbol. So if I'm going to be able to do electron configurations, I have to be able to use the diagonal rule. Now, looking at neon, neon is atomic number 10, so that means there's only 10 electrons. So I don't have to go far down on the diagonal rule to put all these in. Just remember the diagonal rule, the way that we fill. First one's going to 1s. Then you have the 2s. Then the 2p, the 3s, the 3p, the 4s, and then we come back up, 3d, etc. So I'm just going to start putting my electrons in. So first I'm going to go with the first two electrons are going to go into the 1s. So 1s2 gives me 8. Next one's going to 2s2. It gives me 6. After the 2s, I go to the 2p. 2p6. All right, so it's neon is 1s2, 2s2, 2p6. And then the question asks, write the Lewis structure and which electrons are included from the electron configuration. So which electrons does the Lewis structure represent? Valence electrons, exactly right. So the ones that we're interested in showing in the Lewis structure are these valence electrons. These guys are the only ones that we want to represent. So with neon, I'm putting the symbol of the element in. There are 8 electrons. I need to show those 8 electrons, each one represented as a dot. So these 8 electrons represent the octet associated with neon, which is a noble gas. Okay? Question on that one? All right, you've got a mastering chemistry problem, something like that. All right, so next one. Let's go forward. Write the Lewis symbol for each atom or ion, and I'm just going to do a couple of these. So start off with A. So if I look at sulfur, sulfur has how many valence electrons? 6. It's in the 6A family, 6 valence electrons, but it's a -2 charge. What does that mean? Do I add electrons or lose electrons? Add 2. So I add 2 electrons. That means that the 2- anion of sulfur has 8 valence electrons associated with it. So write its electron configurations. I'm going to show the 8. That's the octet. That's stability. And we also need to make sure that we represent that it's charged sulfur, or the anion, so we need to put brackets around it in a -2. All right, let's do magnesium right quick. So magnesium has how many valence electrons? It's in the 2A family. It's got 2 valence electrons. The way I'm going to represent it is just 2 electrons. And again, the book and I don't really see, I think we should represent this like this to represent the electrons that are paired together in the S. The book wants you to show them, and I think Mastering Chemistry wants you to write it out like this too, that you put them in 2 different locations. Okay. with what we're doing with bonding coming up, I understand the purpose of that, but it's really not reflective of the electrons that fill the orbitals. The orbital theory and the Lewis diagrams didn't come out at the same period of time, so they're taught in two different ways. All right, so if we now look at the next one, if it's the magnesium 2+, so with this one, magnesium, we just said had 2 electrons, valence electrons. The fact that it's 2+ charged, what does that mean? Does it add electrons to it or lose electrons off? Lose. So it loses 2 electrons, so minus 2 electrons. That means that it has 0 valence electrons. Okay, so if I think about what it's going to be, you would put no electrons around it. And if you want to show what's really there, if I took magnesium and I took the 2 electrons off, what I'm left underneath it is neon. So in terms of an electron configuration, it's like neon with a 2+. But this is the way that we represent it. All right, so just writing out Lewis structures, understanding those. Okay, now we want to look at a couple of Lewis structures for ionic compounds. So let's start with the first one. I've got strontium and I've got oxygen. So you can look at this a couple of different ways, but if I look at what strontium is as a neutral atom, it has 2 valence electrons. Oxygen has 6 valence electrons. But I know this is an ionic compound, so electrons have been transferred. And these have some predictable charges with them. So if strontium reacts, strontium's in the 2A family, so that means it forms what charge as a cation? +2. Yep. So when it loses its 2 electrons off, so minus 2 electrons, it's strontium +2, and those 2 electrons end up going to oxygen, and when it picks up those 2 electrons, it has a full octet, -2. And all of those work the same way. You lose off the number of electrons so that both the metal and the non-metal have a full octet. All right, question on that? All right, let's keep picking. Okay, so this one's a little bit different. It wants you to use the Lewis symbols to determine what the formula is going to be between the compounds. So let's just do a couple of these. So let's do first, I'm going to do A. So I've got calcium, and calcium's in the 2A family, so it's got 2 valence electrons. And I've got nitrogen. Nitrogen's in the 5A family, so it has 5 valence electrons. So what nitrogen or calcium's going to do is calcium wants to lose those 2 electrons off. So minus 2 electrons to form the calcium 2+ cation. And if I look at what nitrogen wants to do, nitrogen wants to pick up 3 electrons. If it picks up 3 electrons, then it has an octet, just like that of neon above it. Okay, so picked up 3 extra electrons means it's a -3 charge. So I've got something that wants to lose 2 and something wants to gain 3. I've got to figure out the balance so that what a common denominator is going to be between the two is a 6 electron exchange. Okay, and we can think about it the same way we did the crossover rule with the charges. So that means it's going to take 3 calciums to come up with those 6 electrons and 2 nitrogens to come up with those, accept those 6 electrons. Electrons lost have to equal electrons gained. Right? If we look at one of the other ones, that's the hardest one in the group. Let's do, and we'll do B. So magnesium has 2 valence electrons. It's going to want to lose 2 electrons off to form the magnesium 2 plus cation. Right, what's going to happen with iodide? Iodide has 7 valence electrons. It's going to want to pick up 1 to form its octet of 8 electrons. And it has a charge of -1. So I've got something that's going to lose off 2 electrons. To accept those 2, it's going to take 2 iodide atoms. Okay, so this is kind of explaining what we talked about much earlier in the semester, why certain things have fixed charges when they form ions and form at fixed ratios. Okay, all right, so put the compounds in order of increasing lattice energy. So we said, let's talk about quickly with lattice energy. So there were 2 factors that played a role with lattice energy. And the 2 things were the size of the ions, right? So size of the atoms. So size of the atoms. And the second thing was the charge. So the higher the charge, the higher the lattice energy, and the smaller the atoms, the higher the lattice energy. Okay, so highest lattice energy with smallest size and with greatest charge. All right, so we've got 4 things here that we want to put in order of increasing lattice energy. So let's first think about what the magnitudes of the charges are. So what's the charge going to be on potassium? +1's in the 1A family, right? What about the chloride? -1. So +1, -1. Okay, what about the strontium? +2, -2. And the rubidium's in the 1A family, so it's +1, -1. Calcium's in the 2A family, +2, -2. So the ones that are +2, -2, those are the big boys. Okay, the charge is the most important factor. So those are going to be the last 2. So the first thing we want to do is look at the first 2 and find out which one's the least. Okay, so let's take the ones that are +1. So I've got KCl versus rubidium bromide. Okay, so they're both +1, -1. So I need to look at which ones are going to be the smallest and versus which one's the largest. So if I look at the 2 different atoms and compare the sizes, start with the halogens first. So which one's the largest, chlorine or bromine? Okay, so this one's the largest. So that makes it the weakest. What about between potassium and rubidium? Rubidium's underneath potassium. So it's the largest as well. So that means that this is going to be the one that has the weakest lattice energy associated with it. So this can help me start writing some of my things out. So I know this one's going to be first, and then this one's going to be next. Now, if those 2 things had been swapped, so if it were potassium bromide and rubidium chloride, and it wouldn't be a clear answer to that one. Okay, because you'd have one bigger on one side and one bigger on the other side. So that wouldn't have been a good test question to give you. But just recognizing that you've got the size, looking for the ones that are the largest. Now I've got to look at my second pair. So my second pair that I'm trying to decide between is looking at the things that are +2. So I've got strontium oxide and calcium oxide. Well, they both have the oxygens common, so those are the same size. So which one is going to be the largest? The calcium or the strontium? Okay, the strontium is underneath calcium in the periodic table. So it's the largest. That means it's going to be the weakest. So just continue it out. Strontium oxide, calcium oxide. Okay, question on that one? All right, let's look at the next one. This is Bonhoeffer cycle, Born-Haber cycle. We're not going to. And by that, I'm not going to ask you to do that problem. Okay, so we want to start doing as much of these and review as many of these as we can. Write out Lewis structures. So first thing I want to do is go over and review the rules. So I put all those rules that we had on those previous pages up, combine them on one page. So you may want to go back and write this out as something to study with, but you can go back and look at today's class video and write all this. First thing to do is write a skeletal structure. Hydrogen is always terminal. If it's an oxyacid, that means the hydrogen is connected to an oxygen. You make the least electronegative atom the central atom, and we did it for a particular thing that had nitrogen in it. Count the total number of valence electrons for all the atoms that are in it. Add 1 electron for every -1 charge. Subtract 1 for every +1 charge. Number 3 is you attach all of the atoms to the surrounding atoms to the central atoms by making single bonds and subtract the total number of electrons. Number 4 is complete all the octets, starting with the outside and working in, and then recount the number of electrons that you have. Number 5, if the octets are complete, give the extra electrons to the central atom. Number 6 was if the central atom doesn't have enough, you can share, collapse atoms down and make double bonds from things on the outside. All right, so let's, the only way you learn these things is by doing them. So let's look at a couple. So let's start with NF3. So first thing I need to do is find out how many electrons is there, valence electrons. So I've got nitrogen has 5. The fluorines each have, how many? 7 for each one. There's 3 of them, so that's 21. That means I have a total of 26 electrons to put somewhere. All right, the halogens are always terminal. Okay, so that means I'm going to put the nitrogen in the center and surround it by these 3 fluorines. Okay, so the first thing I do is I draw a single bond to each. So there's 3 single bonds that use 6 electrons. So that took me down to 20. The next thing I want to do is make an octet around all the exterior atoms. So on this fluorine, I need 1, 2, 3, 4, 5, 6. Same thing with the other ones. 6 more electrons are 12. 6 more electrons are 18. So now I've used 18. I have 2 electrons left. Those remaining electrons go to the central atom. And now I've used all the electrons up. So that's the Lewis structure for nitrogen trifluoride. And that's the bonding pattern that commonly we want to see with nitrogen. 3 things bound to it and a lone pair of electrons. Okay, recognizing that makes life easier for us. All right, let's do, I need Charlines to HBr. Let's do C. So I've got sulfur it's in the 6A family. So it's got 6 electrons. I've got 2 bromines. The bromines have 7 electrons each times 2. So that's 14 electrons. So if I add right, I've got 20 electrons to share around it. All right, so again, the halogens are terminal. So that means I'm going to put the 2 bromines around it somewhere. So the first thing I do is start with drawing a single bond. to each of the exterior atoms, so that uses how many electrons? I used 4, so I've got 16 left. Now I want to fulfill the octets around the exterior atoms. 1, 2, 3, 4, 5, 6. 6 more makes 12. I take 12 from that. I've got 4 electrons left. Put those 4 electrons on the central atom. Okay? And that's the bonding pattern I expect to see everything that's in oxygen and sulfur. So, whenever I see something that's in the oxygen class family, it's either going to be 2 single bonds with 2 lone pairs, or it's going to be found with a single double bond with 2 lone pairs. Those are the ones that yield a former charge of 0 in the 6A family. And it doesn't matter if it's oxygen, sulfur, selenium going down the table. That's the common ways I expect to find it.
How you set the atom that goes down?
Electronegative.
Electronegative, so
Yeah.
they're always
No. No. And we'll look at some structures. We've got a lot of these to do. Okay. So I chose about 10 of these problems to do. All right, so let's look at the next set. So sometimes you have to figure out what goes there. Now, I guess I would say when you write structures that have carbon in them, typically if it's something that has one center, you describe that center atom first. But as soon as we start describing things that have multiple centers, I mean, if you look at most things, if you have one center, that's the maximum you can put is 4 atoms on it. So there's molecules in nature that are thousands of atoms. So you've got lots of centers. So you have to work your way through it. It's not as easy as saying that first one's always the center one. Okay, so let's do this guy first. Let's do A. All right, so we're going to treat it the same way. I got carbon, which has 4 valence electrons. Hydrogen has 1 each times 2, so that's 2 valence electrons. And then oxygen's in the 6A family. It has 6 electrons. 12 if I counted right. All right, so if I look at carbon and oxygen, I know hydrogen's terminal. Carbon and oxygen, which one's going to go in the center? Oxygen's electronegativity is 3.5. Carbon's is 2.5. So carbon's going to go in the center. The least electronegative one's going to go in the center. Okay. Now, where do I put the hydrogens around it? Because there's so few atoms here, this is where you've got to do some trial and error. I'm going to start with putting the hydrogens connected to the carbon and then to the oxygen, see if I can make it work out. So make single bonds between everything. Okay, if I make single bonds, how many electrons did that use? Use 6 electrons. So now I've got 6 left. So now I fulfill the octets around the exterior atoms. The only thing that needs electrons is the oxygen. Hydrogen has its duet. It's already happy. Okay, so I put 6 electrons around the oxygen, and I'm out of electrons. So does that a full octet around everything? What's lacking? Carbon doesn't have all the electrons it wants. So what I do is I collapse a pair of electrons down and make another double bond. Okay, so when I do that, I move those electrons down. So now does everything have a full octet? So if I look at the electrons, this has its 2 around it, its duet. This has 1, 2, that's 4. A double bond, that's 8, so it has an octet around it. This has 4 electrons and a double bond, that's an octet around it. So it gives me a stable structure. Okay? All right, let's try the next one. So let's do, let's go ahead and do B. So B says it's C2 CL4. So carbon has 4 times 2, that's 8 electrons. Chlorine has 7 times 4, that's 28. So somewhere I've got to put 36 electrons around it. Okay, so if I compare carbon to chlorine, carbon's going to be central. There's 2 carbons, so I'm going to put those 2 carbons next to each other, and I'm going to surround everything with the chlorines. So I've got 4 chlorines. I'm going to spread them out symmetrically. So I'm going to put 2 on each one of the carbons. Okay, so let's just start making some bonds. So 1, 2, 3, 4, 5. 5 single bonds that use 10 electrons. So I've got 26 left. So less 26. Now I start to fulfill the octets of all the exterior atoms. So I've got 1, 2, 3, 4, 5, 6. 6 more here. 6 more here. That's 18. 6 more here. That's used 24. Less 24 leaves me with 2 electrons. Ooh. Okay, so I've got 2 electrons. Put it on a central atom. Where do I put them? Okay, so I could put it on one of the central atoms here, but still that's not going to give octets to everything, so I'm going to collapse those electrons down and make a double bond. So those are gone now. And now when I do that, is everything have an octet. The carbons have 8 things bound to them, 8 electrons on both carbons. The chlorines, I missed a set of electrons. They all have 8 electrons around them. Everybody has an octet. All right, let's do a couple more. All right, so determine which ones would be pure covalent, polar covalent, and ionic. So again, you're going to get the electronegativity table. You're not going to get this table on the test, but you're going to get the electronegativities. You'll get this exact grouping. So what we're doing is looking for a difference in electronegativity and see where it falls. All right, and again, the way that I describe these is that pure covalent is equal to a difference of 0, and then covalent, and what the book calls nonpolar covalent, would be 0.1 to 0.4. Polar covalent would be 0.5 to 1.9, and then finally ionic is going to be where you have things that are a difference 2 or greater. Okay? All right, so you just simply look at the electronegativities and figure out where you are. So I've got 2.5, and I've got 3.0, so the delta, 3.0, the delta negativity, electronegativity is 0.5. So if it's 0.5, where's that fall? That's a polar covalent. All right, nitrogen and sulfur. So nitrogen and sulfur, nitrogen's 3. Sulfur rolls in at 2.5. The difference is 0.5. Exactly the same thing. All right, potassium and fluoride. This one's, I don't even have to calculate it to know what this one's going to be. So potassium's 0.8, fluoride's 4. The difference 3.2. That is definitely ionic. All right, nitrogen and nitrogen. Anything that's the same means the difference is going to be 0. So that would be the pure covalent. Okay, those are the easy ones, because you just have to look at the table. Now, the thing I'll tell you, you're going to have to answer some of these on the final exam, and you're not going to get the table. So you need to understand some trends that are going. But frequently they're going to give you things off this top row. And just realizing, if you'll realize what's going on in the top row, 4, 3.5, 3, 2.5, 2, that 0.5 step, that goes a long ways to help guesstimate some electronegativities. And everything below it, they just keep getting a little bit less and less typically as you go down. Okay, more Lewis structures. So let's do A. So I've got 4 hydrogens, and each one has 1 valence electron, so that's 4. I've got a carbon in there, so 1 carbon, and it has 4 valence electrons. And oxygen comes in with its 6, so 14 electrons. Now, the order that this structure is written out tells me something about how the atoms are attached. Okay, the fact that the 3 hydrogens are next to the carbon tells me that they're surrounding, and the O with the H tells me that that hydrogen is connected to this. Otherwise, if it wasn't, these hydrogens would all group together. Okay, and this is actually a functional group called an alcohol. We talked about functional groups way back in chapter 3. But whenever you see an OH bound together, that means it's an alcohol. So carbon's going to be central. I'm going to put the 3 hydrogens around it. I'm going to connect everything with a single bond. That takes 1, 2, 3, 4, 5 single bonds. So that used 10 electrons. I've got 4 electrons remaining. So if I look at what's remaining, does the carbon have an octet around it? It does, so it's happy. So I need to look at the oxygen. So I put those last 4 electrons around the oxygen. Now it has its two single bonds and 2 lone pairs, what oxygen wants. That's its bonding pattern. That's a stable Lewis structure. All the electrons are used up. Okay. All right, let's do bro. All right, so bromine has 7, oxygen has 6. The fact that it's -1 charge means that it has 1 more electron. So it also has 14 electrons around it. All right, just 2 atoms. They're somehow connected to each other. Okay, so if I start trying to put these together, single bond in between the 2, that gets rid of 2, so I've got 12 left. If I use the 12, I put an octet around each. That uses all 12 electrons up. So in this case, the bromine has an octet around it. Does the oxygen have an octet around it? And because it's a -1 charge, I'm going to represent it like that. So the oxygen has 8 electrons around it as well, but it's not a common way that we would find it. And if I would look at what its formal charge was, we're going to kind of put formal charges a little later, I'd find that this has a formal charge of a -1. So is that the most stable form of oxygen? No. In this structure, that's the way it's found. And that's a very reactive compound. It's a very powerful oxidizing agent. Right. So more of these Lewis structures. So, okay, so let's do the top one first, and then I'll let y'all choose the different. Okay, so I've got 6 hydrogens. I've got 2 carbons. That's 8. I've got 1 oxygen. That's 6. 20 electrons. Okay, again, the order of the atoms in this structure tells me that I've got the carbon on the exterior. surrounded by hydrogens. And an oxygen in the center. Okay, I just want to start single bonds, 2, 3, 4, 5, 6, 7, 8. So I've made 8 single bonds that used up, is that right? 1, 2, 4, 8 single bonds. Yeah, that used up 18 electrons. Did I do my math right?
Yeah.
Oh, thank you. 16 electrons. That leaves me with 4. Those last 2 go around the center atom. Now everything has a full octet. It's called an ether. Yeah. So whenever you have a carbon bonded to an oxygen bonded to another carbon, it's called an ether. Probably the most common one that we use for household use is diethyl ether or starting fluid. Use the surge tractor. Or any diesel motor. Okay, let's look at one of the polyatomic ions. Let's do C. Nitrogen has 5. Oxygen has 6. There's 2 of them, so that's 12. And it's a -1 charge. That's 1 more. 18 electrons. Okay, so which one's going to go center? Nitrogen or oxygen? Least electronegative is going to go in the center. Okay, so start with single bonds. 2 single bonds uses 2. We've got 14 left. Okay, so that would be one way I could write it. All right, that's used 12 electrons up. And then the last 2 electrons are going to go on the central atom. Okay, so if we do that, that would get rid of all the electrons. So that is one of the Lewis structures I could write for this. It's a -1 charge. All right, can you think of another Lewis structure I might write? Okay, so let's collapse one of the electron pairs down. So let's rewrite it. And collapse one of the electron pairs down. Okay. That gives the preferred bonding pattern to oxygen the way it wants. Okay. And that gives the octet. So this one doesn't have the octet to the nitrogen, so it's not going to be a preferred way there. So this is certainly going to be more preferred. What would happen if we collapse another electron pair down? Another double bond, but how many electrons would be around the nitrogen then? Okay, so if we do 2 double bonds, that gives us 8, but we've got a lone pair there already that gives 10. That's too many. So we talked about in the notes, or I talked about in the notes, some things can do expanded octets. These guys can't. In the 2A family, they can't ever have 10 electrons around. If you go down 1 row, they can sometimes, but those can't. All right, so that means that this is going to be our preferred structure. It's not going to be that one. Okay, because this one gives us octets on everything. And if I were to look at what formal charges were, just to make sure that this makes sense, this is the bonding pattern observed, so its formal charge is 0. You can check that out if you want to. This one is a formal charge of 0, and this is a formal charge of a -1. So I've got 0, 0, and a -1, and it equals the charge of the polyatomic ion. And that's what we expect to see. Okay? All right, so now what I want to do is start playing, write ones that fulfill the octet rule. And this is going to be the challenge on some of these. And then if it has resonances available, I want to use formal charges to each of the atoms to find out which one is the most probable structure. Okay, so let's do a couple of these guys. So let's start with A. So I've got chlorine has 7 electrons. Each oxygen has 6. There's 3 of them, so that's 18. And it's a -1 charge, so that gives us 1 more. Put that together, I got 26. So I did it right. All right, so it's 26 electrons. All right, 26 electrons. All right. If we look what's going to be in the center of this one, this is where it's kind of a, who do you put there? Oxygen was 3.5. Chlorine's a little bit less than that, so chlorine's going to go in the center. So I'm going to put the chlorine in the center. I'm going to surround it by the oxygen. So 1, 2, 3 single bonds. That gets me down to 20. Now go around the exterior atoms. That uses 6. 6 more is 12. 6 more is 18. So less 18 takes me down to 2. The last 2 are going to go to the central atom. Okay, so that gives everybody an octet, and again, that's a minus 1 charge. Okay, everybody has an octet there. But that's not the bonding patterns I typically like to see. Okay, because usually oxygen doesn't want to be in this way. So it tells us to do the formal charges. So let's do the formal charges to see if this is going to be a preferred. All right, so the formal charge on this one, we've calculated this one already, it's a -1. So oxygen single bonded with 6 electrons around it's -1. So all of these are a -1, -1, -1. So let's figure out what it is on this chlorine. So the chlorine's valence number is 7 less the 2 less 1/2 of 6. So what's that come out to? 3 plus 2. Is that right? Yep. And that adds up because I've got -1 3 times, that's a -3, and plus 2 -1, it adds up. But again, the most preferred structure is going to be the ones where all of them are zeros. And then if they're non-zeros, you want to get the most negative number on the most electronegative atom. And that's not what we have in this case. Okay, because the most positive number is on the chlorine. I want the most negative number. So that's not going to be a good one. So let's try to do something else. Let's try to now collapse in a lone pair. So let's go back, take those same electrons in, and I'm just going to collapse this lone pair at the top to make a double bond to the chlorine. Okay, again, it's a -1. So this is the bonding pattern that oxygen wants. So let's put its formal charges on here. So these are still -1 and -1, but this one now becomes 0. So, well, that's the bonding pattern for what oxygen wants. Okay, so oxygen wants 2 things bound to it and 2 lone pairs. And we can calculate it out right quick. So it's 6 minus the 4 electrons less 1/2 of 4. It's 0. Okay? But whenever you see something obey those bonding patterns, preferred bonding patterns are always 0. It's just a shortcut that you learn to do. All right, so let's calculate what it is for the chlorine. So the chlorine is 7 less the 2 less 1/2 of how many bound electrons to the chlorine? How many? 8, right? So if I do that, that gives it to be a +1. So this guy's +1. That's better, okay? It's not maybe the most preferred, so let's try something different. Let's collapse another pair of electrons down. So all of these are different resonance forms that you could have. The only thing difference is I'm making more double bonds. Now that's getting to be a lot of electrons around the central atom. Okay, but let's see what the formal charges tell me. So this is a formal charge of 0. This is a -1. This one's 0. That's better for me, but let's look at this chlorine. So it's 7 minus 2 less 1/2 of how many electrons are bound to it. So 4, 4, 2, 10. It's a formal charge of 0. So now that is an expanded octet. It's got more than 8, but when you go one row down, these guys are sometimes. So those are allowed to have that many electrons around the central atom. So of these 3 Lewis structures that I've drawn, and I could draw another one where I collapsed another lone pair down, but then it would go out of balance. Okay, which one's going to be the most preferred out of those 3 that I've drawn? The last one, because the last one has the 0. It's got the most zeros of everything. So we're looking for the Lewis structure that has the most zeros on the formal charges. That's the most stable one.
Why don't we add a non-bonding pair from
Okay. Understand what you're asking. Say it again.
I don't really understand what I'm asking either. So when you keep adding bonds to it,
Okay, I'm collapsing electrons in from the exterior.
from
Yeah.
the outside. So why does 2 lone, or the 1 lone pair not do anything? Why does it just stay?
Well, it's everything. All the electrons have already been assigned to the exterior atoms. If you're going to have expanded octets, it's always different. So those were the extra electrons left over from fulfilling the octets of the exterior atom. So those were the extra ones. Any extra electrons go to the interior, always. Okay? All right. Let's see if we can, and that was one problem. All the other ones work similar there. Let's finish up on this guy. So use the formal charge to identify the best Lewis structure. Again, we want a Lewis structure that's got zeros. So that's preferred. So let's figure out formal charges. So hydrogen terminal is always 0. But let's figure out for this sulfur. So sulfur is 6, less there's 0 bonding, less 1/2. There's 4 things bound to it, each with a single bond, so that's 8 electrons. So that one's +2. All right, now let's look at this carbon down below it. So this is going to be the carbon atom. So carbon's 4. It has 4 unpaired electrons, less 1/2 of, we've got 2 single bonds, 4. So this one, it's a -2. So +2, -2, everything adds up to 0, so that's a possibility. All right, let's see what it is on the other side. So let's look at this carbon. So it's 4 less 0 less 1/2 of, I've got 4 single bonds, that's 8 electrons. That one's a 0. Look at the sulfur. 6 less 4 for the unpaired electrons, less 1/2 of 4, 2 single bonds, is 0. Which one's preferred? One with the zeros. Well, the fact that it's more electronegative really doesn't tell you that. The thing that I would look at this and tell me that that's not the bonding pattern carbon's going to have, that's the key thing that tells me something's wrong. Carbon wants 4 things bound to it, and that's the only way carbon is found in nature. It's 4 things bound to it. All right? Okay. We'll continue with this one. All right. So I encourage y'all to find some enthusiasm to finish this semester out with some strength or some gizmo or go or whatever you want to call it. From my perspective, it looks like you're asleep. Make sure you get chapter 10 notes by Thursday.